All right, let's talk about the mole.
Mole.
No, not that kind of mole. Nope, not that mole either. The mole in chemistry is a very important concept, and it's very different from the moles that you might be familiar with. Before we can talk about the mole, let's take a look at the guy who began the research that led to its discovery. His name was Amadeo Avogadro, and he lived in the latter half of the 18th century and into the first half of the 19th century. There he is. Kind of a severe-looking guy, if you ask me, but brilliant. Avogadro was a lawyer, but he was also very interested in mathematics and science. And he built himself a lab and began to experiment with gases. He came up with a very important idea. It's now called Avogadro's hypothesis. But his idea was this. He said if you have two containers of gas, two different gases, and the gases have the same volume, and they have the same temperature and pressure, then they will contain the same number of particles. Now, he had some math to support this. But remember, science in the 18th and 19th centuries was very rudimentary, and so it was a little difficult to prove. It took many years of research after that to finally come up with our concept of the mole. Avogadro was the first person, though, to start to think of gases as composed of particles, which is pretty impressive for the time. Now, after many years of research, including people like John Dalton, who we've heard about, Berzelius, Proust, Boyle, Jacques Charles, we finally came up with a definition for what a mole is. A mole is defined as 6.02 times 10 to the 23rd representative particles. Okay? That number, 6.02 times 10 to the 23rd, was named after Avogadro. Avogadro had already been dead. This was the latter half of the 19th century. He had been dead for almost 50 years at that point. But out of respect, they named it after him posthumously. So, what is a mole? A mole is simply just a way of counting things. Counting particles that are so small that you can't even see them, and that are so small that you need a lot of them to actually visualize a substance. So it's a count. Think of things like words like dozen, or a ream of paper, 500 sheets. A dozen eggs is 12 eggs. A gross of something is 144. Those are words that represent numbers. Well, that's all that a mole is. It's a word that represents a very big number. Now, how big is this number? All right, 6.02 times 10 to the 23rd. It doesn't look that big. It's only a few digits long. But if I were to expand it out, I get this. 602 followed by 3, 6, 9, 12, 15, 18, 21 zeros. That's 602 sextillion. That's a big number. It might be hard for you to figure out or imagine how big that number is. How big is that number? It's huge. I mean, it takes a while just to write it down on paper. Never mind how many things is that. Let me give you some examples of how big that number really is. If you had 1 mole of rice grains, 6.02 times 10 to the 23rd grains of rice, it would cover the surface of the earth to a depth of 75 meters. 75 meters is about 225 feet. That's how deep the rice would. We'd all be crushed in rice, which would be uncomfortable to say the least. However, you don't have to worry, because that many rice grains is actually more rice than has ever been grown on this planet in all of human history. We haven't even reached that number of grains yet. That's how big the number is. If you have a laptop, it probably has a processor in there, if it's one of the newer ones, that performs at a speed of 100,000 megaflops. A flop stands for floating point operations per second. So what that means is if you asked your laptop to count, it could count up to 100,000 in 1 second. That's how fast your processor is. If you had your laptop count up to Avogadro's number, it'd take just over 380,000 years. That's how big that number is. And that's at 100,000 megaflops. That's 100 billion counts per second. Your laptop can count up to 100 billion in 1 second, and it would still take it 380,000 years to get to Avogadro's number. That's a big number. It's huge. So how much space do you think that many atoms of iron would take up? Well, there's a picture of it. That's 1 mole of iron. It's not very big, is it? That's just a regular old flask. And that little bit of brown, gray powder in the bottom, that's 6.02 times 10 to the 23rd atoms of iron. How about a mole of water? There it is. Just about 18 milliliters worth of water. Mole of sodium chloride, table salt, that's it. So what does that tell you about the size of the particles of these substances? If I can have so many in such a little amount, they must be really, really small, right? That's why we need such a big number, because these particles are tiny. They're so small that we need that many of them just to be able to work with the stuff. The mole is important. It's the central unit in chemistry. We use it as a count. It's a way of counting large number of particles that we can't see. Remember, 1 mole is 6.02 times 10 to the 23rd particles. That's important. That's a relationship that we're going to need over and over and over again. And I'll give you an example. Okay? Before we do our example, we want to understand what we mean by particles. All right? We're talking about particles of a substance. All right? It's the smallest piece of a substance that still has the properties of that substance. So depending on what kind of substance you have, you're going to have a different particle name. For example, if you have an element, the smallest piece of an element that still has the properties of that element is called an atom. So the representative particle of an element is an atom. If you have a molecular compound, the smallest piece of that still retains its particle is called its properties is called a molecule. And if you have an ionic compound, we call the smallest piece of an ionic compound that still has its properties a formula unit. So those are the particles that we'll be using. We won't actually be calling them particles. We'll be calling them either atoms, molecules, or formula units, depending on what type of substance we're dealing with. Here's an example. I want to calculate how many atoms of gold is Au, that there are in 1.54 moles. So I know how many there are in 1 mole, 6.02 times 10 to the 23rd. So in 1.54, I just must have to multiply that by 1.54, right? Yes. But we're going to learn a new way of setting up the problems, something called unit analysis. And if you learn how to do this when we have simple problems like this, then when we get more complex problems, it'll be easy. You'll have already trained yourself how to do it. So here's what I want you to do on your paper. We're going to solve this, okay? I want you to draw a cross that looks like this, okay? I'm going to draw a little cross. And in the upper left quadrant of this little cross, we're going to write the number that was given to us in the problem, 1.54 moles, okay? And we're not going to write anything underneath it. Although if you had to, you could write a 1 under there, but you don't have to. In the upper right-hand quadrant, we're going to write Avogadro's number. And the reason we're going to write Avogadro's number is because the question that I'm being asked is asking me to solve for to find out how many atoms. And so I want the thing in this upper right-hand corner to have the unit that I'm looking for, which is atoms. Now, underneath 6.02 times 10 to the 23rd atoms, I'm going to put the equivalent measurement to that, which is 1 mole. I know that because 1 mole is equal to 6.02 times 10 to the 23rd atoms. Now, the reason I'm putting that on the bottom is because what I have created here are 2 fractions, essentially. Well, a whole number and a fraction, or a single number and a fraction. When I multiply fractions in math, I'm allowed to cancel anything that shows up on both the top and bottom of 2 fractions. You see the word moles on the left there and the word mole underneath on the bottom? Well, I can cancel the word moles out because of where they are in this little example here. And so now all I'm going to do is multiply 1.54 times 6.02 times 10 to the 23rd and divide by 1. Now you got to be careful in putting this into your calculator. If you're putting your calculator and you're doing 6.02 times 10 caret 23, you will get the right answer for this one, but for the next example you won't. I want you to get used to using the exponent number, and I'll show you that in a little bit. When I multiply 1.54 times 6.02 times 10 to the 23rd, I get 9.27 times 10 to the 23rd. So that's the answer. Let's do another one. How many moles of water would contain 2.75 times 10 to the 24th molecules? Remember, water is a molecular compound, so its particle is called a molecule. I want you to draw the cross again. And this time we're going to put, again, the number that's given to us in the problem goes on the left, upper left. 2.75 times 10 to the 24th molecules. Now, on the right, the unit I'm trying to get to, the unit my answer is supposed to be in, is moles. Okay? So I need to put that on top. Moles has to be on top. And I've got molecules to start with, and I need to get rid of molecules. Well, the relationship that we're working with here is always the same. 1 mole is equal to 6.02 times 10 to the 23rd molecules in this case. So now I put 1 mole on top and molecules on the bottom, 6.02 times 10 to the 23rd molecules on the bottom, so that I can cancel out molecules and leave myself with just the unit of moles on the top. Now here I have to divide. If you consider these to be both fractions, I'm going to divide 2.75 times 10 to the 24th by 6.02 times 10 to the 23rd. Now if you put this into your calculator using the times 10 and the caret, you're not going to get the right answer. You're going to come out with something times 10 to the 46th or 47th power, which is the wrong answer. What I want you to do is get used to using the exponent button on your calculator, okay? You'll hit the shift button, and then look for the EE. That's the exponent button. That will allow you to put in the exponent, okay? And I'll show you this in another video. So I divide 2.75 times 10 to the 24th molecules divided by 6.02 times 10 to the 23rd molecules. Molecules cancel out. I get 4.57 moles of water, okay? That's kind of it. It's not very difficult, this level of calculations. But they're going to get more interesting. So learning how to do the unit analysis setup that I'm showing you now is going to save you a lot of time and frustration in the long run.